This is Lab 5, Create Your Own Lab. The purpose of this lab was to observe the motion of Felix Baumgartner as he jumped out of a balloon above the Earth's surface at an altitude of 38,969.3 meters for Red Bull Stratus. I created a computational model of the motion based on initial conditions given by the observational data on the Red Bull Stratus website. I also observed the effects of change in density and temperature as a mass fell through various levels of the Earth's atmosphere. The summation of the results found that Felix did indeed break the sound barrier at 843 miles per hour, which was also his maximum velocity. The observational model and the computational model had slight differences, which will be discussed later on. The fundamental principles involved in this lab included two forces, the gravitational force and the drag force. These two forces were used together to update the velocity and position in our computational model using Newton's second law. To calculate the drag force, we needed to find the density, the drag coefficient, and the surface area of our mass. To calculate the density, we first used the altitude at which our mass was to calculate the temperature, and in turn use that temperature to calculate the pressure, and using that pressure, finally, to calculate the density of the atmosphere at the point the mass was. Here's a graph that shows temperature and pressure changes as altitude decreases. Using data points from Red Bull Stratus' website, I was able to create an observational graph of Felix's motion. The blue line represents the altitude as he descends, and the red line represents the magnitude of speed. Using these data points, I was able to gather initial data for the computational model. For the initial velocity, I used 0, 0, 0, and for the initial position, I used 38,969, 0. I created 4 different while loops. 3 of the while loops represented different levels of the Earth's atmosphere that Felix traveled through, because each level is going to have a different drag force when calculated, and a 4th one because the parachute is also going to cause a change in the drag force. The final slowing motion was caused by Felix deploying his parachute. This is the graph created by the computational model. The blue line represents the velocity, and the red line represents the temperature of the atmosphere. When the graph of the computational model and the graph of the observational model are compared, we find that the main points all fairly line up, but the points in between don't. We can guess that this is mainly because the points in the observational model, the red line, the points in between the main points, are estimated rather than computed. Here are some reasons that might account for the differences in the computational and observational models. This wasn't easily seen in the models, but when you look at the data, the parachute caused the drag force to increase by a much larger scale in the computational model than the observational model. Next, in the first minute of the jump, Felix began spinning. The observational model took the added angular momentum into account, while the computational model didn't. And last, the temperatures realistically don't change at the even scale used in the functions to calculate the temperature of the atmosphere in the computational model. For example, in the lower stratosphere temperatures don't usually stay at a constant negative 56.46 degrees Celsius, which can be seen here in the Earth atmosphere model. For the summation of results, Felix did indeed break the sound barrier, which was also his maximum velocity. In addition, the observational model and the computational model had slight differences that can be accountable for by less generalization between the points in the observational model and other components of forces, such as the spin and angular momentum.